Hello everyone, so here's a quick update on my PhD research so far, called Can Commercial Supercomputing Fast Track Our Careers? And on this slide I've got my supervisors and my sponsors acknowledged there. Now I just want to start off by showing you a chart, a pie chart from a survey that was carried out by the AusSRC in 2020 of radio astronomers in Australia. And it's this one question from that survey is, where do you process your data? And about 30% of people just process their data on their own laptop or desktop computer, but obviously most people have got much bigger data than they can do that, and they're using PAWSY or AusStar or NCI, or alternatively they're using a computer that's provided by their university or their research institute like that. So large, publicly funded, publicly provided computing installations. And if there's anybody using commercial supercomputing, then they just show up in this little 3% other category up there. Now just hold that thought, because I'm going to go on to bring in something different, which is the discussion of the trends in the high-performance computing industry. And this is data from the top 500 survey, which is a biennial survey going back to 1993. This basically shows that the top supercomputer in the world, this orange line up here, the computing power is basically going up still exponentially. There was a bit of a break around here, but it's... And then the blue line is the number 500 performance computer in the world. Now, back in 2011, the people who are working on the SKA, there's a lot of concern that the science data processor for the SKA had a higher computing requirement than what was actually available at that time, and it was going to be, too much computing power that couldn't be provided in Australia. In actual fact, the industry caught up. So by their target date, it could have been managed by among the largest supercomputer in the world. But then due to kind of delays in the construction of the SKA, the current estimate of the power required for the science data processor over here, with its implementation date around about 2028, is well within what's achievable within the top 500 supercomputers. So there's a bit of a lesson about exponential growth. So it's what happens behind your back when you're not really looking, and you can find out that what you thought was an insurmountable problem suddenly becomes looking pretty ordinary after just a few years. Now I want to go on to show you another chart which uses that same data, but I just plotted some extra information on here, because I want to. The first thing is the yellow lines there is Photonics, a system you might be used to, and the Photonics phase 1, phase 2, which is in there. It's in the top 500, although it doesn't meet the requirements of the SKA SDP, so it's going to need to be replaced or upgraded or something if it's going to play that role. Now, on this chart here, I've plotted the incursion of commercial systems. So back in 2019, there was one commercial system in the top 50 of the top 500, basically a cloud provider. So as a private company owns the computer and they're selling access to time like that. If you look today, November 2024, there are 10 commercial systems in the top 50 of the top 500. And in fact, the highest one of all, which is a cloud provider, their machine is more powerful than what the SKA SDP is planned for. So again, the idea that this computer requirement is going to be insurmountable is very, very difficult. We're already ahead of that just in terms of what's available commercially. You don't even have to buy your own computer. You can rent space on it from someone else. So this prompts the thought for my research question, really, which is, how do we get access to these increasingly important commercial computing systems? 10 out of the top 50 and the top 500 are commercial. So what would have to happen for radio astronomers to effectively use commercial supercomputing? And those of you who've been around for a couple of years would have heard some of my earlier talks on the subject, and you'll know that I've been doing quantitative research using a couple of studies in radio astronomy, processing the data at Doug over in Kings Park Road to research this very question. Well, the last year or so I've been doing some qualitative research, which is more sort of social science stuff, some in-depth interviews with astronomers and HPC experts, and using a technique called thematic analysis to figure out what their experience can tell us about the future of commercial supercomputing in radio astronomy. That thematic analysis produced a lot of themes. There's a lot of information in there, so I can only just really scratch the surface here, and I've just highlighted 4 of the major themes that are raised. The first one is that everyone who'd used the commercial systems had a positive experience. They like the availability, the machines are available 24/7, they can choose what node, how much memory to use, they're not stuck with one particular infrastructure. And basically they can, because of those things, they can get a shorter lead time between having an idea, doing a data processing and getting a publication. So that's the bit that's going to supercharge your career, you know, because effectively it allows you to get more publications per year. That's the concept here. But there's a few kind of barriers and roadblocks along the way that need to be addressed. And one is that you need access to more advanced computing skills than are generally taught to physics graduates in Australia. And one potential solution is for everyone just to stop using Python because it's not really HPC oriented, and learn to use Go or Rust or something like that. Another suggestion is that vendors should provide support for optimizing your code for a supercomputer, and that should be perhaps rolled into the price of the time rental on the machine. Or alternatively, academia could set up an HPC team to help astronomers make their code more HPC optimized. And it was pointed out that SRC is potentially doing some of that work already. Another major theme is that costs and funding are not aligned. So when you get funding for a research project, it doesn't generally include dollars that you can go to purchase time on a commercial supercomputer. And finally, almost everyone agreed that software is becoming a big problem. So, for example, if you want to move your whatever software you're using, you want to be able to optimize it on multiple different commercial systems so you can jump around and pick the machine that's most economical or easiest to use for you. That's a big difficulty. I mean, just as one simple example, if you're using CASA or WS Clean, you know, who's going to pay to port that software to make it GPU compatible so you can use it on a high performance GPU machine, for example. So software is a big problem. It's something for the community to work on and come up with a model for supporting the software for the community. So that's just a very quick taster of some of the themes that come out. I've got a paper in the late stages of preparation. Hopefully you'll be submitting it to a journal before Christmas. So you may be able to read it early next year and see a lot more information on those themes and some other themes that were raised as well. Or alternatively, if you've got any burning questions about it, you can ask me right now because I'm more than happy to answer your questions.